want to welcome you to another statistical or machine learning class. Um, Before I get started today, um, I'm actually going to say I've been recording and of course I've been posting lecture videos on my YouTube channel. Okay, I think it's up to date. So make sure in case you want to watch the recording, to give you another opportunity for what you miss. Of course, you're going to find out on my YouTube channel. Okay, so today we're going to focus on density based spatial clustering of application with noise. Okay, uh, that we normally represent with DBSCAN. In the outline, I'm actually going to have a review on different kind of hard clustering that we've done this week. I'm going to have a review of on K-means. I'm going to have a review on K-medoid. I'm also going to have a review on hierarchical clustering, okay? Because having a recap on that will enable you to make a connection between different kind of hard clustering that we're going to be talking about. And of course, after that, I'm going to introduce you to what I call the topic of the day. Okay, the density-based spatial, clustering. I'm going to talk about how the algorithm work. I'm going to talk about the evaluations, and of course, it's also going to come with limitations. Then how do we use this in R? I'm also going to walk you through that. So what I advise that you should do is stay back, listen. If you need if you get stuck and you need clarification, then you ask your question. Okay, so I want to first start with review on K-means. And I'm going to use one example today that cut across. I'm going to talk about crime. I seriously appreciate any man or woman in uniform, whether the police uniform or in the military. But today I want to talk about, we'll focus on the police. Police don't just go out. Okay, you may find yourself doing research with police, like consulting, you may be their statistician, or you may be their machine learning expert, advising them, or providing statistical or machine learning information, guiding their outing. They don't just go out. I want to actually have a review on K-means. How can you use K-means algorithm? Okay, for instance, I want to use a robbery data in Chicago, a city of Chicago, as an example. Okay. If you look at in the city of Chicago, if you want to use a K-means, okay, you want to partition crime incidents, okay, in all locations, in the city of Chicago. So using the K-means, of course, you could partition that into three, using your elbow. Of course, with the K-means, we normally start with initial number of clusters that we're going to have. Okay, so let's say you make use of elbow, or you make use of gap statistic, or you make use of Shiloh, and at the end of the day, if you arrive at three clusters, okay, the three clusters, one of them may be downtown Chicago, okay, the other cluster maybe at the west side, the other cluster may be at the south side. Now you have three clusters. Now in each cluster, okay, there's going to be centroid. Now the question is, how do I compute the centroid? The centroid is the average. How do I get the average? Of course, when you have your data, okay, every crime committed, they collect data based on time, the date, the latitude, and the longitude. So the centroid now would be the average latitude and the longitude of the crime location. So what is going to serve as the centroid now will now be average crime location. So police will be patrolling average crime locations. They're only going to be patrolling three locations. And those three locations, they are centroid. They are average. Okay, that is for the K-means. Now, what about the K-midroid? Okay, in the K-mean, the centroid is the average, but in the K-midroid, because of the fact that mean could be sensitive to outlier, if there's an outlier or noise, okay, K-means is not going to do a great job. Now, what the K-midroid is going to do instead of using the mean, is going to use the actual crime location. It's going to randomly assign other crime incidents, okay, to maybe any three randomly choosing crime location. Okay. Of course, if I want to talk about burglary data in the New York City, okay, maybe I'm actually going to have three midroid. I could have Brooklyn as one of the midroid. I could have Manhattan as one of the midroid, and I could have Queens. Have anybody been to Queens in the New York City? Okay, I could have that as one of the midroid. So at the end of the day, the police will be patrolling the real crime scene, not the average. The average one will be for the K-means. Okay, the actual one will be for the K-midroid. Now, but here, the K-midroid is robust to any outlier. Okay, what is an outlier of event? Maybe something happened far away. Okay, if we have a crime incident far away, and if that is a one-off event, okay, that is an outlier. Okay, the K-midroid we actually classify outlier well. Now I want to move to the hierarchical. Okay, I still want to use crime data. Okay, but uh, this time around I want to go to Los Angeles. I want to use assault data in Los Angeles. Okay, and I want to use hierarchical clustering. Okay, I actually want to use a hierarchical clustering to cluster, assault data in the whole Los Angeles. Now, let me take a look at this. We have two types of hierarchical clustering. We have agglomerative, okay, and the other one. But we focus on the agglomerative in this class. The agglomerative hierarchical clustering is we're actually going to begin, okay, where each assault incident will be in their own cluster. Every assault incident will be in their own cluster. Okay, when they're in their own cluster, what is going to happen next? We now start merging them. Okay, we're going to start. This is the way we're going to do. We are actually going to start from small neighborhood in the LA. Maybe I'm starting from Hollywood. Hollywood could be one of them. Compton could be one of them. Okay. And of course, downtown LA could be one of them. Then I start from small neighborhood. I'm now start merging to a bigger region. Okay. Bigger region where I'm actually going to have the North LA versus the South LA. And at the top level, what is going to happen at the top level, you're actually going to see all the crime incident in one cluster. And that is, we normally you make use of a dendrogram. And at the top level, we have a way to cut. Now, the police will decide where to cut, whether they want to cut at city level, or they want to cut at neighborhood level, or they want to cut statewide. Police don't just go out. They are movement. They are, for them, before they can go out, they are guided statistically. Okay, you know what? And I want to move to a new algorithm. What are we missing? Why is this algorithm that we want to talk about today become very important? Is because the other three algorithms that we've talked about only consider spherical shapes. Situation where we have irregular shapes. Okay, then the conventional algorithm, the algorithm we've talked about, may not be able to handle irregular shapes of cluster. Okay, and that is why the density base, okay, we handle that. Okay, now this was introduced by Esther et al. In 1996. And the essence of this is, okay, can we actually situation where we do not have a regular clusters, okay, where we expect the shape of a cluster to be convex or spherical, and if it is not, okay, the k-means, the k-midoi, the hierarchical clustering may struggle with that, and we don't want to mislead. And that's why we're going to consider the density base. And let me also tell you this: where there's an outlier, okay, k-means, k-midoid, and the hierarchical, there's possibility, okay, they may not be able, they're actually going to classify outlier into a cluster, but the density plot will not, the density base that we want to talk about now will not actually classify outlier. Imagine a crime occurring in a wrong in an highway far away from the city. Okay, that is not going to be classified. That is going to be seen as a one-off event or as a noise. But the other conventional algorithm will classify them. Okay, so now, and that was why I say it's robust to outliers. Robust to outliers is not going to classify outliers, it's going to dictate that this event is just a one-off event. And police, they don't really need to waste their resources patrolling that kind of place, because it's a one-off event. It's not something that occurs frequently. Okay, now, but let me tell you this: we got parameters. If you want to use a density-based clustering, okay, we got parameters that need to be considered. Okay, let me tell you this: the essence of using this algorithm is to be able to identify, for instance, I'm talking about crime data the other time. Can I actually cluster, can I identify cities with the high density of crime? Can I identify city with the low density, with the medium density? Can I also identify city with an outlier where, it is not a common occurrence, it's just a one-off event? Okay. Now, if that is my vision, of course, I'm actually going to use a density-based clustering. But let me tell you this: we got parameters that we need to consider. Number one parameter is what we call EPS. We have to, if we want to actually cluster observation, you need to have a radius. So that is what we call the radius of the neighborhood around the data point. If I'm going to classify, okay, objects, or I want to classify observations, or I want to classify city, or I want to classify household, I need a radius. Okay, they have to fall within the radius. Then after that, another parameter that is very important is what we call the minimum samples. Like, before we can actually form a cohort, what is the minimum number of households required to form a cohort? I have to consider that too. And that's why I said the minimum number of data points we want in the neighborhood before we can define a cluster. That needs to be decided. And let me tell you this: these parameters are very crucial. If you don't choose them wisely, okay, if you don't choose them wisely, then you're actually going to mislead. Because the EPS, which is the radius, around the neighborhood, and the minimum number of observations, actually play a crucial role. And that was why I said for each instance, the algorithm counts how many instances are located within the what? Within the radius. Okay. And not only that, you have to decide on the minimum number of observation that you're gonna cluster in. Now, we got some important points that we normally consider. We call that core points. Core points. Okay. When the minimum samples, are satisfied, then those ones are going to be called, those observations are going to be called core point. And that was why I said the minimum sample points are the minimum number of neighborhood a given point should have, okay, before they can be classified as a core point. Okay. Then we have a border point. When you take a look at the border point, let me tell you this, the border point are within the radius, but they do not have a, the minimum number to be classified into a cluster. At times when I'm driving out, when I'm driving within Minnesota, and there are some neighborhood outskirts of Minnesota, okay, those neighborhood, they are the border points. Even though they are within the radius of Minnesota, but they are not going to be classified. Okay, they don't actually, qualify to be the core point. They are the border point. And that was why I said they are within the radius of the core point, but they do not contain the minimum neighbors to be able to be classified as a cluster. That's why they're going to be called border point. Now, we also have the noise that we also call outlier, that we call anomaly. I was telling you the other time when you talk about a crime, situation whereby something occur in a city that it is not, it's not a frequent occurrence. Can refer to that as an outlier. Okay, so we're actually going to have a noise. Okay, a noise is not a core point, it's not also a border point. And I'm going to show you right now. Please pay attention. Pay attention. Look at the red. Can you see the red? Those are the core points. Okay, but look at the yellow. The yellow, they are at the border point, even though they are within the radius. Look at that. This very guy. Oh, okay. 1 second. I'm gonna use my pointer. Now take a look at this guy. Okay, if you take a look at this guy, it's within the radius of this particular guy, but the fact that it does not have the minimum number of neighborhood to be classified as a core point. Okay, this are the border point. This is also at the border point. This is like talking about the outskirts of a city or of a state. Okay, but take a look at this guy here. Oh my God, this guy is a noise. This is a noise. So this picture here actually show you the typical example of a core point, of a border point, and of the noise. Okay. Now I want to move. Now, well, every because this is an algorithm. Okay, the density-based clustering is an algorithm. We expect the convergence time. Okay, that is what the worst case scenario is going to be n squared. Okay, and of course, you know, the overall average is going to be n log n. We are talking about the convergence time that is going to happen. But let me tell you this. The other time I was talking about spherical. This is what I mean by spherical. Okay, when the cluster is like this, then K means K midroid, hierarchical, they're actually going to do a great job. But look at a shape like this. Look at a shape like this. A shape, where you're going to have within, you can say you have a cluster within another cluster like that. K means K midroid, they're actually going to perform woefully here. For this kind of arbitrary shape, you need a density-based cluster. Okay, take a look at another example. Okay, if you take a look at this is using the k-means, but look at what k-means is saying. K-means is classify all the green. K-means is saying they're going to be in the same cluster, the green, the red, but that is not true. Okay, but take a look at the density base. The density base is going to say, okay, this guy is in a cluster, this one is another cluster, this is another cluster. So when you have a shape where you have something inside, like this is an arbitrary shape. Okay, Kemi is not going to do a great job. Go ahead. You mean what is going to be the reshape? Like the weirdly shaped like points. Like wouldn't it get the group correctly, like hierarchical with the I forgot actually I understand what you mean. Do you know why the k-means and the k-midpoint will perform woefully in an arbitrary shape, because the distance they're going to compute is either Euclidean or Manhattan. But density ball doesn't do that. And that was why, so if you take a look at this, if you look at in terms of closeness, of course, this green, they are very close, but this is not a good cluster. I mean, this is a wrong way to do that. So because the k-means actually using the minimal distance, just like what you said, but we also have to put into consideration the shape. So so what I'm displaying right now, okay, is that the density plot, we correctly identify that the density plot is not based on the minimal distance. It is not based on Euclidean distance, but it is based on one, okay, what is it? You define your radius for core points, then you decide how many neighbors, what is the minimum number of neighbors that can form a core point. That is what that guy. So this is trying to show you that k-means is not good algorithm for classifying cluster that look not spherical, but it's only good for spherical. And what we need to use there is the density base. Okay. Now take a look at this. You have stuff like this. This is the data set. Okay. And if you use k-means here, what makes it irregular? This guy, right? When you have a shape inside another shape, that is irregular. The k-means may not be able to handle that. Okay. Now, but I'm going to do something. If I use k-means, k-means is going to cluster all of them, including noise. But density clustering, we actually identify noise. It's not going to cluster noise. Now I'm going to do something now. Let's go to the arrow code and see how it works. Okay. Now I want to use data, but I want to deliberately use data that have a multiple shapes. Does that make sense? K-means k-midpoint will not be able to undo that, right? I deliberately want to do that. Okay. And you know what? The multiple shapes with 1 and 2. Okay. I set a seed. Okay. Then I want to have 5 clusters with not the number, I want to do that 25 times. Okay. Now let's see. Do you know, if you take a look at what I'm showing you now, okay, it's like k-means is, if you use k-means, what has happened? K-means have cluster all the point, including the noise. K-means is not good for this. You actually going to mislead when you use this. Okay. Now I want to walk you through different kind of irregular shapes. Okay. Take a look at that. So irregular shapes. Okay. Now I want to quickly move. Okay. I said something here. Unlike k-means, we do not require, we don't need to specify number of clusters ahead of time. K-means k-midpoint, we need to specify numbers of clusters ahead of time. Okay. We say does not require the user to specify the numbers. Okay. And let me tell you this. This algorithm can find any shape, whether regular, circular or not. Okay. And it can also identify outliers, because the community pay police. Okay. And the community don't want to waste resources. Okay. If there's a one-off event of violence in a particular city, okay, they don't want to waste their resources. They just want to say, okay, that's an outlier. But with the k-means algorithm, with the k-midpoint, you may not be able to identify that. They're going to cluster all of that, and before you know, they're going to tailor resources, towards that. Okay. Now this is the package. Okay. Now, now let's take a look at this. Here, I'm trying to say minimum points to be classified is 5. You have to decide. We also have a way to determine optimally that minimum point. Don't forget, we need that. We also need to specify the radius. Okay. Now, I need you to pay attention to this. The data, our data is in matrix form, right? Arranged in row and column, right? And of course, the EPS we talk about the maximum distance, the reachability maximum distance. Okay, the MIPT talk about the minimum number of points to be classified. Okay, then we're also going to scale our data. You remember, we don't want situation where a particular variable will dominate. We're also going to scale. Okay, and of course, we have three type of method that we can use within the DBSEN. We have the distribution one that treat that treat data as a distance matrix, and we have the raw. The raw one we treat data as a raw data, and we have the hybrid. Okay, that expects raw data but also calculate the partial metrics. Okay, let's work on this now. Let's see results. Are you ready to see results? Take a look at this. Okay, now using the DBS, do you see dots, the black dots? Those are the noise. The DBS is not going to classify them. But K means we classify them, and you will waste resources. Okay, we don't want to waste resources. You see the classification now. Okay, any point that is not clustered is a noise. If you take a look at that here now, we actually have noise. Okay, you can see the one in green. You can see the one, you can see that guy, you can see the one in blue, you can see, even though we have how many clusters? We have 5 clusters. Okay, but I'm going to say plus the noise that we did not cluster. The DBSEA is not going to cluster that. So situation where the incidents of crime or look irregular, be shape. Okay, the algorithm that we're going to recommend to the police is DBSEN. It's not going to be K-means. Okay, now I need to pay attention to this. Okay, this is it. Can you see that now? This is the way. This is, if you want to see that in another form, can you see that? Okay, you have 5 cluster. The black dot the black dot is the noise. Okay, those are the noise. Okay, now you know what I want to do now. I want to print the DB. I really want to know if I have, take a look at this. Please pay attention. I have 1,100 incidents. I want to classify them. Let me give you an example. Maybe I have 1,000 incidents of crime, 1,100 incidents of crime, and I want to classify them. In the classification, I need to first tell the world what is the minimum number of incidents that I can cluster, together. Minimum. It could be more than that. Okay, it's okay. 5. At times we use domain knowledge. At times we use domain knowledge to be able to decide on the minimum point. Then the radius. We also use domain knowledge. A statistician working on spatial analysis. Okay, they're going to use the knowledge of the geography to figure out the radius. Okay, now, oh my God, I want to explain this now. The classification has been done. Let's take a look at that. 5 clusters. When you see cluster 0, it's no cluster, it's noise. It means 31 out of the 1,000 incident is a noise. Don't worry about it. It's a noise. It's a one-off event. Okay. Now, when you take a look at, let's take a look at cluster 1. Okay. In cluster 1, we're actually going to have those one that are core points. We're also going to have those one at the border. So here, how many at the border? 24. Of course, we expect the number at the border to be less than the number in the core areas. Does that make sense? So 386. Okay. As a core point, 24 in the border. Take a look at that. So in the respective cluster, from cluster 1, 2, 3, 4, 5, this is going to give you opportunity to know the number of observation in each cluster and those ones that are noise with DBS. Let me tell you this. The other algorithm may not detect noise. In fact, they're actually going to classify noise in a cluster. How are we going to waste our resources on that? Okay, I'm going to move right now. Now, I said there are two parameters that are very, very crucial when you are actually using the DBSEN. Okay, the minimum number of points and the radius. Okay, and I said here, the idea is to calculate the average of the distances of every point to its k nearest neighbor. There's a particular algorithm in machine learning, we call it KNN. Has anybody heard about KNN? Okay, so they use that. Okay, now then the values of k will be specified, okay, by the user, okay, and correspond to the minimum point required. And the next is to figure out what will be the optimal EPS parameter. And of course, we can actually determine that as well. We use a threshold. Okay, take a look at this. Okay, this is using the KNN that I talk about. Okay, the KNN, well, we make them to have, an idea of what the required parameter is going to be. Okay, now here I'm starting with the data. The data is the DF. Okay, and I specify K to be equal to 5. But to use the KNN, at least I have to predetermine, specify a particular K value. Now I'm going to show you something now. Take a look at this. Okay, this actually cuts here. Can you see where it cuts? Okay, like it's 0. Maybe 0.15. Okay, so this is to have a sense of what the radius is going to be, because the radius matter. Okay, so we don't just choose that value arbitrarily. Now, I want us to use DBSAN algorithm away from crime data now. Has anybody seen a data set before that we call IRIS data? Okay, thank you so much. The IRIS data have 4 different species. Okay, we got 4 different species. That was why you say 1 to 4. The Setosa and so on like that. And of course, the IRIS data have, I think it's collected across some variables like SEPA length, SEPA weight, and so on like that. Okay, but you know what we want to do with the IRIS data? Okay, I want to use the DBSEN, and I want to use the idea of KNN plots to figure out, the parameter that are needed. Okay, how am I going to do it? Take a look at this. I set a seed. Okay, I set a seed. Okay, and of course, I settle for this. 0.4 and 4. Maybe 4 is the minimum number of points that can be classified as core, and the radius is 0.4. So that radius you can come out if you actually maybe you use the KNN, neighbors to figure it out, or you use a domain knowledge. Okay, and at the end of the day, you now want to generate. Take a look at this. That is what it's going to generate. How many clusters do we have? 4. This is confirming to us we have 4 species. And with some noise. The noise are the black dots. I told you the DBSA will not cluster the noise. Okay, can you see noise? Okay, the black dots. And let me tell you this. There's also a possibility. Okay, you see this guy here, right? A black dot inside. Even if the black dot is inside the cluster, it's going to flag it out. That's a noise. Does that make sense? A noise could be inside, a noise could be outside, but it's going to flag it out. Okay, it's going to flag it out. Okay, that's what I wanted to see. Okay, now I said something here. Due to its distance-based calculation, the DBSA suffer from the cost of dimensionality. Let me tell you this. Why do we have more than one technique? Because every technique has a drawback. Okay, so I want to identify the drawback of this dimensionality issue. Because take a look at this. This is like I'm using two dimension here. Okay. What if in my data, if the data is multivariate, have so many features. Okay. And we actually want to use we need to use a dimensionality technique before we can project the data points in the high dimensional space to lower dimensional space. Okay, so that is one of the drawback of this. I said the DBSA cannot cluster data sets well with the large differences in density, because with that, there are going to be large differences in density. Then I said, because the minimum sample EPS combination cannot then be chosen appropriate. At times, we may not choose them appropriately. Okay, the two parameter, the moment, the quality of your result depends on your choosing the parameter value, the EPS at the minimum number of points. So you need to be guided. Okay, our models are not failing us, but we are the one that we are in a hurry, that we don't do the right thing at times. All these models, all this algorithm, make sure when you are using model or algorithm, make sure you know the weakness of the model and the algorithm. Okay, don't only focus on the strength only. Also focus on the weakness. And what you're going to be doing is how you can overcome the weakness. You'll be able to overcome those weaknesses if you actually choose the right parameter. Okay. Now I said, now let me now tell you this. I need you to pay attention now, because this guy is what is going to, is one of the limitations that will now, trigger us to consider alternative algorithm. Look at that. Okay, DBSCAN cannot cluster data set well with similar density and when there's a significant overlap in the distribution. Let me tell you this. The algorithm we'll be doing from Monday, they are add clustering. Okay. What I mean by add clustering is that a particular observation can only be in one group. It cannot be in more than one group. But what of in a situation where there's an overlap? Okay, I'm going to tell you an overlap in crime. Okay, if somebody commits offense in Wisconsin, I also run to Minnesota and commit offense. There's an overlap. Okay, it is not just going to be a police from one state that will be involved, but police from two states. So in that kind of situation, we're going to talk about probabilistic assignment, which is going to be soft. Does that make sense? So the density base clustering and K means K middle, they are for add clustering. Okay, situation whereby an object or observation can only be in one group. The moment you are in this group, you can't be in the other group. But what if in a situation where there's an overlaps? Okay, when there is an overlaps, okay, then we're going to be talking, that is what we want to talk about next. Oh my God. Statistical machine learning is like a story that goes on and on and on and on. We don't just do what we do. We got a reason why we do what we do. Now, we want to consider a situation whereby there's going to be an overlap. Where there's an overlap, there's something that we call probabilistic assignment is going to be involved. When the probabilistic assignment is involved, then you're going to be talking about mixture of distribution. And that is what is going to take us to Gaussian mixture model based algorithm. Is there any question for me today before I go? That's all I got. Enjoy your weekend. See you on Monday. Bye for now, everyone. You're welcome.